How is the goodness of fit test related to the speed limits in Denmark? We'll see that in just a minute. The goodness of fit test is used to test whether our observations, our data, distributes itself on different categories according to a hypothesized distribution. So our null hypothesis would be that the observations follow this or that distribution. Let's call it distribution X. It could be a normal distribution, a Poisson distribution, any distribution. It doesn't even have to have a name. For example, here we have an opinion poll made among the Danish electors, the Danish voters, and you can see how many percent would vote for each party in the parliament. So the bright colors represent the opinion poll, and the dim colors represent the last election. And we might have a hypothesis that says that the voters are going to vote the same way they did at the last election. So the dim colors here represent our hypothesized distribution, and we would like to test using a goodness of fit test if the opinion poll is the same as our hypothesis. Does the opinion poll follow this distribution that our hypothesis mentions here? Or is it too different? Does it deviate too much, more than we can explain by random effects? That's what the goodness of fit test is out to decide, really. Another way to illustrate this is the Galton board. The Galton board is a board which has a small reservoir here of tiny metal balls. And when we flip the board upside down, then of course the balls will start to travel downwards, and doing so they will meet a lot of obstacles here, and they will bounce off these obstacles here, and you know, the itinerary of the individual ball is pretty much unpredictable. However, you can do some probability computations as to where the balls are likely to fall in these different categories. We can treat these as categories. So let's see what happens when we run the video. So what we can see here is that the balls pretty much found the categories according to this normal distribution that we have here. However, there are some deviations. Some of the categories have more balls than the distribution predicts, and some of them have less. And we can use a goodness of fit test to see if they actually do follow this distribution. That is, these deviations can be explained by random effects, or does this actual distribution that we see here, does it actually deviate from the hypothesized distribution? In this case, I would say that they're pretty close. So a goodness of fit test at some significance level, 5%, would probably conclude that the balls do follow this distribution. And now we're ready to talk about the speed limits, because I imagine we make a questionnaire, an opinion poll among Danish car drivers, or just Danes in general, to see if they think the speed limits in Denmark should be changed. So that's the question we ask, and we allow the answers to fall in two different categories, either yes or no. So we don't allow for don't know. And we have a null hypothesis, and let's say that the null hypothesis is that the answers will follow an even distribution. So that is, we expect there to be equally many yes and no sayers to this question. That's just an hypothesis. That might not be right, that's just what we set out to test. So then we actually go out and ask people, and it turns out that we get these results. 102 said yes, 78 said no in our poll here. So we can imagine that we're just pouring these little green balls into these two categories, and we expect them to distribute themselves evenly because we pour them, we let them fall as raindrops. So according to the null hypothesis, these balls are just pouring down here all the way into our categories, and they should have equal probability of landing in yes and no. However, in our experiment, it turns out that we have more in the yes category than we do have in the no category. So I'm just not going to draw all of these balls, just illustrate it doing this. So that was the experiment. This was what we actually observed, but we also had an expectation, and that expectation would be that we would have gotten equally many in both categories. In other words, we would expect to get 90 and 90 because we do have 180 answers altogether, so we expect this distribution, and we can sort of draw that over here. So we would have expected 90 balls in each category if the null hypothesis is true. So how do we decide if it's true or not? In other words, is the result we obtained, is that too far away from what we expected? So far away that we would reject the null hypothesis? Or is it something we can explain by random effects? And as always, we need to compute a test statistic. And in this case, the sensible test statistic is the sum of the squared deviations between the observed and the expected quantities here, like that. So we sum over all the categories. In our case, there are 2. So we find this number here, the observed minus the expected, squared divided by the expected. We do that for the yes category, and we do that for the no category, and add them up together. So what we get is this, like that. And when you compute this number, you get 3.2. So what does that tell us? Not much, unless we know how this test statistic is distributed. And it turns out it has approximately a chi-squared distribution. So what we have to do is to compare this number to a chi-squared distribution of a certain number of degrees of freedom. So we compare that to the quantile of a chi-squared distribution, which has well, let's say the 95% quantile, and it has degrees of freedom k minus p minus 1, where k is the number of categories, in our case 2. P is the number of parameters computed using data. That's a little tricky, so let's dig into that a little bit. I mean, the number of categories in our case, that's 2. It's pretty easy. We have yes and no. P, well, for a normal distribution, let's say our hypothesized distribution was a normal distribution, then we would use the data to compute both a mean and a standard deviation. So P would be 2. For a Poisson distribution, we would use the data to compute the mean of the Poisson distribution, so we would use the data once to compute this number here. for an even distribution like the one we have here, we don't really have to compute any parameters, because just from knowing that we have two categories, we immediately know that we expect 50% of the observations in each category. Let's say we had 10 categories, then we would expect 10% in each category. And we would do that just knowing that we had 10 categories. We don't need to see the data to compute these expected values here. So in our case here, for the even distribution, p is equal to 0. So the quantile that we're looking for here is one that has a distribution with 2 minus 0 minus 1, so that's 1 degree of freedom. And we're looking for the 95% quantile. We use Excel to look up that quantile. So I say here equal to chi square inverse 0.95% and 1 degree of freedom. And I get this quantile out, 3.84. So that's the number we have to compare our test statistic to. And we can see that our test statistic is actually inside the exceptions region. So the chi-square distribution looks something like this for 1 degree of freedom. And it turns out that the quantile that excludes 5% is at 3.84, but our test statistic here is inside. It's probably around here. So in other words, we cannot reject the null hypothesis. This sample here, this opinion poll here, does not provide evidence to reject the null hypothesis. So we can still accept the fact that, or we can accept the hypothesis that there's 50% among the Danes that do want to change the speed limits and 50% don't.